Okay, welcome everyone to this inaugural lecture of Professor Brad Karp. So it's a great occasion when we're able to celebrate the promotion to professor of one of our number, and it's great to have a great audience for that occasion, and to dress up appropriately. I hope you're suitably impressed. So I just want to give a little bit of background on Brad's history, and then I'll be handing over to perhaps a little bit more colorful background that you will hear from Michael Wolfish, yes, Professor. So I'll start by just giving a little bit of history. Brad graduated in 1992 in computer science at Yale University. He then went on to do a PhD in which he graduated in 2000 at Harvard under the supervision of H.T. Kung. His work was in geographic routing for wireless networks and was very interesting and innovative work. He then spent 3 years in the networking research group at the computer science department at University of California at Berkeley, before moving to Pittsburgh, where he actually had an interesting joint post between the computer science department and the Intel research lab, also on the campus at CMU in Pittsburgh. Then in October 2005, he moved to UCL, and he arrived with the Royal Society Wolfson Research Merit Award, and has been here since. So one of the interesting features of that visit was that he, at the interview visit, met his now wife. And this may have been an interesting tactic, because it certainly may have clinched the deal in terms of bringing him here. And maybe we can learn from that in future recruitment processes. Since being here, Brad has made a major contribution to the department in so many different areas. Of course, primarily in his research, which has continued to prosper and flourish. And he is now head of the Systems and Networks Research Group. But in addition to that, he's involved himself in a number of aspects of both the college and the department. I'll just mention the PhD recruitment process that he has attempted to bring us into a much more fearsome and high-quality standard of recruitment. And this is ongoing work that I believe is helping us enormously. He's also improved the whole process of student feedback, questionnaires, and how that's handled. And in so many other areas, he's able to give us interesting perspectives and advice. So I think, it's really a great moment, as I said at the beginning, when we're able to celebrate the promotion to professor of one of our own number. And on this occasion, I think Brad is one that I really feel has been a long time coming, and it's really fantastic to have Brad here, able to give his inaugural lecture. Long time coming, partly because it's been a while since he was promoted, and we are waiting for this lecture. But I'll finish there and hand over to Professor Michael Wolfish, Associate Professor at New York University, who would like to say a few more words of introduction.
It's a deeply felt honor to introduce Brad Karp, who has been a guiding light to me and many others. As John said, Brad was an undergraduate at Yale and a graduate student at Harvard. Less commonly known is that for his first 3 semesters at Yale, Brad was in their highly selective theater studies program, and that at Harvard, Brad served as a resident tutor where he was beloved by the undergraduates in Dunster House. I was one of those undergraduates, and since that time, I have racked up a vast debt to Brad. He presented academia as a path to me, which I had known little of, gently encouraged me to do a senior thesis, advised that thesis, pointed me to a meaningful job afterward, guided me to graduate school after that, and then coached me in my role as a faculty member, all the while showering me with insight about our field about what it means to do great research and about how to live one's life. Brad achieves this influence by, first of all, insisting on quality. And by quality, I mean coffee. So Brad asked me to speak here just so I could bring him freshly roasted beans from New York City. So I have actually done that for him. That was a joke. Okay. Joking aside, Brad's thoughtful devotion to quality and standards has changed lives. Peter Marchenko, who received his PhD in 2013 from UCL as Brad's student, describes his advisor as a, quote, outstanding mentor whose ability to understand, analyze, and improve students' work is exceptional. Peter goes on to say that Brad was my role model while I was learning how to do research. Whenever I faced an obstacle, I asked myself, what would Brad do? How would he approach this problem? He taught me how to take on problems which may seem to be unsolvable. Of course, many faculty cultivate their students, but it's often out of self-interest. Brad's mentorship stems from a deeper, purer place and has much broader impact. Dayan Stefan, who's a PhD student at Stanford and worked with Brad on the exciting COWL project, writes, Brad has had a big influence on me and my research. His emphasis on vision and precision has guided me to important problems and novel solutions. He has treated me as one of his own students and fought alongside me in the trenches. I've yet to meet a student that he's worked with, myself included, that doesn't want to grow up to be like Brad. Brad's righteousness goes even further. As one of many examples, his reviews, written under double-blind anonymity, are mini advice manuals that selflessly tutor anonymous authors. Some of you know what I'm talking about. This conscientiousness and these standards of taste and behavior have inspired me and many others. Eddie Kohler, professor of CS at Harvard, wrote, Brad is a model of generosity and commitment to a certain ideal vision of the research life, and if I didn't know him, I might not have this job. I love him. David Maziere of Stanford calls out Brad's skill at research brainstorming. Robert Morris of MIT is, quote, delighted at Brad's academic success and his excellence as a thoughtful and generous friend. But I want to conclude with my NYU colleague, Professor Jinyang Lee, who was never a co-author of Brad, nor a student, nor a friend, but she knew Brad when she was a graduate student, and she said this. In research, I think there are two types of mentors, and then there's Brad. The first type shows you where to cast the fishing line to maximize the chance of snagging a fish. The second type teaches you how to catch a fish by going in the water alongside you. And then there's Brad, who not only does the above two, but also will show you how to cook a great meal with the fish so that it's irresistible. Brad has taught me a tremendous amount. She goes on to say, his advice and insights have made me a better researcher and a better person. To that, I say amen. And now I am very happy to turn this over to our advisor, mentor, teacher, counselor, group head, husband, father, friend, scholarly inspiration, and mensch, Professor Brad Karp.
Thank you very much. Well, it's very hard to follow that. I hope to convince you that it's all false by the end of this. Thank you very much, John and Mike. As I look out in the audience, it's wonderful to see all of you. I see family. I see friends. I see a surprising number of intellectual property lawyers who I hope are here as my friends, and colleagues from near and far. You'll see that a point that features later in this talk is that regardless of the distance between two parties, there may or may not be a connection, and I'm delighted that you're all here today from near and far. So I want to start by making a dedication today, and that's just to all of the students, interns, and RAs I've worked with over the years. Before I started as a researcher, I sort of knew and expected, like most graduate students did, that the thing that would be rewarding would be to try to articulate interesting problems and work hard on them and try to come up with insights that were enjoyable to make. What I didn't completely understand is that that is at least equaled by the joy in working with students and interns and RAs and helping them try to find in themselves what's going to lead them to succeed. And what I mean by that is really sort of their inner nature. Some of them are mathematically gifted. Some of them are fantastic programmers. Some of them are fantastic at expressing themselves and conveying ideas. Some of them can't stand expressing themselves and turn that into a strength in their research. Because they say, oh, well, it would be so complicated to explain this. I think what I'm going to do is just come up with something simpler that will do the job as well, and then their research gets better. So the point is, they've all been very unique, and it's been a pleasure and privilege to work with every single one of them. I'm very grateful for the opportunity to have done that. And so the story that we're going to be talking about today is, well, the internet works. We've connected the world's computers, and there are billions of internet users. This is an obligatory plot of the number of internet users, just below 3 billion now by year. And you'll be glad to know that this was precisely measured on July 1st each year at this scale. That's very important. Not only that, but those billions of internet users run convenient networked and cloud-based applications that they love. Right? So like if you want to manage your money in the United States, at least, you can use an application called Mint, which goes and to all of the websites for all of your bank accounts and pulls in all of the data from all of your bank accounts and produces graphs of how you spend all of your money and how you earn money, hopefully. And this is extremely convenient, and everyone loves it, and this is the world we live in now. So, mission accomplished. You can't have a talk by an American without some sort of, oh my God, is he one of those people? So the real story for today is actually somewhat different. We've connected the world's computers, but there's another billion devices. People call them things, the worst name for a research agenda I've ever heard, the Internet of Things. I want to convince people you don't know what you're doing, are coming, and how to cope with that scale of devices, that sheer number of devices. There are billions of internet users, but there are billions more coming, and it appears that they're mostly going to be coming on wireless networks. And if you're a typical wireless network user, you might not enjoy that experience so much. You know, how are we going to cope with the scale of traffic, with the volume of data that people want to send over wireless networks? But even more perplexingly, what have we done? We connected the world's computers. So we made our embarrassingly poorly built and poorly understood software remotely attackable. And we took sensitive data from people all over the world and put it in the cloud and the web browser and created focal points for attacks on privacy. So we've connected the world's miscreants to the world's computers, right? But the subtext for today, which I hope will come out during this talk, and is, you know, it's easy to talk about research, but hard to talk about what makes your area what it is what are the strands of systems research? I consider myself a systems researcher. And so I'll try to articulate and highlight today what the strands of systems research are. One is designing for scale. What I should say also is when I describe these strands of systems research, how many of you have had, if you're a computer scientist, a dinner conversation that goes something like this? So, Brad, you're in IT. So this will be very cathartic for me to explain, and maybe you can use some of this in some of your dinner party conversations. One aspect of a strand of system research is designing for scale, trying to make things very big. And this basically is about algorithms, like old school big O algorithms. So, you know, big O measures of storage, computation, and network load. And so this really brings theory into systems. You can also design for robustness, which means trying to think about worst case inputs to the thing you're building, which is really a form of adversarial thinking, actually. You're going to build something and somebody's not going to try to break it per se necessarily, but what's the worst thing someone could give to my system in terms of it working well? And what I would say is that in the systems area, there's no sharp distinction between robustness and security. Some security researchers will tell you, oh, security is this unique area. Systems researchers have been thinking about robustness for a long time. Security is just a form of robustness. And so adversarial here, yes, you could mean that somebody's trying to deliberately break your system. But adversarial could just mean challenging, a challenging workload. And you need also, when you're designing for robustness, this is very dear to me and important to me, you need to exercise doubt. What that means is you look at the problem and you say, am I really solving the right problem? maybe I should have defined the problem differently. And my colleague Anthony Finkelstein offered me, when I described this to him, this wonderful phrase of science within the frame of engineering. That you've got an artificial problem definition that doesn't come from the natural world, and then you're going to try to prove fundamental things within that frame, but your frame might have been wrong. And finally, you might want to design for the performance of the system that you build. And this requires tremendous attention to detail of the huge amount of stuff, software and sometimes hardware in a system. And we teach our undergraduates that abstraction and modularity are great things, and that the secret of building big systems is that you create something, it has a well-defined interface, you forget about what's inside and layer something else on top of it, forget about what's inside that and layer something else on top of that. And that's how you build. And unfortunately, that is a disaster for the performance of the system as a whole. Systems research is about owning that whole stack and understanding the complexity of it and trying to make sure that the system as a whole performs well. I would say that the attraction of detail is what got me into computer science. Somehow, for some reason, when I looked at computer systems, even when I was a child, I wanted to know how all of the parts worked and how they fit together and how they interacted. And I'm still gripped by that obsession today. So let's get to the first part of the story today. How are we going to scale wireless networks in devices and capacity in the systems approach? So to explain this, I need to explain to you a little bit about how the internet works, and in particular, how you deliver data to devices on the internet. So imagine this is a piece of the internet here, and we've got each black dot is a computer or router on the internet. We've got a source and a destination. The source wants to communicate with the destination. And each router has some unique identifier. Think of it as a number. And every piece of data packet that you send is stamped with the identifier of the final destination, D in this picture. And so every router needs to forward the received packet that it receives. And so, if I'm at S, where do I forward? Which of my neighbors do I forward to? So I'll pick one. He'll have the same question, and so on, until you hopefully get to the destination. And so how do they make these decisions? Well, basically what happens is the routers are going to chatter among themselves about the map of the entire network in some way. And what's going to happen is eventually every router either eventually learns the map, literally the whole map of the network, every link in the network. Let's say there are L of them. Or it learns something about each node in the network. Let's say there are N of those. So the amount of memory, the amount of state that every router needs to think about is O of N or O of L. Okay, it's the scale of the whole network each router needs. Doesn't this sound unscalable? Does your iPhone need to know about every computer on the internet, a piece of information about every computer on the internet? Does it need to learn every time a link fails in China? Does your iPhone need to learn about it in order to have an accurate map so it can forward packets? So the answer is no, so there must be something else going on. And indeed there is. The secret to scaling internet routing is what's called address aggregation, and it goes like this. Imagine that each dot is not one computer, but an entire campus, like UCL. And what we're going to do is assign addresses to the computers inside the campus that start with the same prefix. And now, when somebody forwards, they're not looking at the whole address, they just look at the prefix, which basically is equivalent to UCL. And now, if you do this, every node only needs to think about, in its state, the number of sites, the number of campuses like UCL in the network. You can think of this as driving on a long-distance drive. If you're driving from Los Angeles to New York, when you're in Los Angeles, you don't see signs about the streets in Manhattan. Right? You see signs about New York, the East Coast is this way. That's a form of aggregation. Okay? So the internet does this. What if we want to come up with the most extreme version of scale for routing we can come up with? So imagine that you want to scatter mobile sensors that move around, or things, or vehicles, devices. And you scatter them, say, in the surface of the ocean. They're all moving around. It turns out that mobility and unplanned deployments of computers break address aggregation. Because everything's moving around, you can't make sure that the things are co-located, all have the same address prefix. Okay? And so what this means is, in mobile networks, if you have huge collections of devices, are we doomed to have this tiny little device that might have, because you made it super small and super low power, are we doomed to say that every device has to know about the whole network map or every node in the network? And so this first strand of algorithmically driven systems research, is about geographic routing, a system called GPSR, Greedy Perimeter Stateless Routing. And the central idea is quite simple. It's just that nowadays, machines can know their geographic positions. So maybe what we should try to do is route using geography instead of the unique ID of each node. So it's quite simple. Just inside every piece of data you send, stamp the packet with the location of the destination. And let's assume every node knows its own position. When I said this in 2000, people said, don't you think that's a little bit edgy? Positions. And now, everybody's phone has a GPS. My watch has a GPS, right? You can also do other things. If you have Wi-Fi in your building, our colleague Kyle Jamieson has shown that you can use Wi-Fi itself to figure out where nodes are inside a building. And so nodes know their own positions. So what are we going to do if everybody knows their position? Well, what you can do is have everybody just announce periodically, this is where I am, and its neighbors will hear it. And if you do this, everybody knows where its immediate neighbors are. Okay? And so then you can sort of see the algorithm forming in your head already, maybe. If I'm here, and I've got a set of neighbors nearby, and this is all the neighbors I have in this dotted circle here, we'll just make a sort of hopefully optimal, but maybe not choice. We call this greedy. Locally, it seems like I'll pick the neighbor of mine closest to the ultimate destination, forward to him. And in this picture, if we keep doing that, we'll reach the destination, right? So it seems pretty good. Of course, the neighbor must be strictly closer than you are, or you'll loop, right? Because then if he picks the closest, you'd then be the closest if he wasn't strictly closer than you are, and loop's bad. So unfortunately, this talk is not now over. So greedy doesn't always work. And you can consider this vexed me for about a year, this picture. You're here. There are two perfectly good paths to get to the destination. The geometry is a little bit hard to visualize. The circles are there to help you. But basically, W is slightly farther away from D than X is, as is Y. So when you look just one hop away, you don't see, if all you know is your one hop neighborhood, you don't see any path to the destination. Right? So we give this a name, since it's a problem. We'll call it a void. It's when the circle there centered at D and the circle there centered at X, their intersection has nobody in it. That's a void. Right? So, how are we going to walk around these things? It would be cool if we could figure out how to walk around these things, but only know about, have every node only have to know about one hop away from itself, or we blow our scaling. Right? So how do you do this? So there's this old idea, I'll tell you just how old in a moment, called the right-hand rule, which is sort of a little bit like keep your hand on the wall in a maze. I did not come up with this. I'd heard it in a lot of places. And actually, when I was discussing this work, as I was doing it with Scott Schenker, I told him that I needed to find a citation for the right-hand rule in a paper I was writing. And he said, oh, this sounds like computational geometry. I know a computational geometer. I know Marshall Byrne at Park. I'll set up a call for you guys. I'm a graduate student. He's an extremely famous computational geometer. It's not even my area. I get on the phone with him, and he said, what's your question? I said, I'm looking for a citation for the right-hand rule. And he laughed at me. He laughed at me. He said, that's folklore. There's no citation for the right-hand rule. He said, when caveman computational geometers were sitting around the fire, that was what they talked about. So folklore, the right-hand rule. It goes like this. If you have a picture like this, let's say I'm arriving at X. I rotate counterclockwise about myself until I hit the first edge there. Take that, go counterclockwise about myself again. You get the idea. This will take you on the tour of this so-called face, this enclosed region. Right? And this is great, because it only requires you to know the positions of the people one hop away from you. Unfortunately, that doesn't work that well either. So take this graph, which interestingly has crossing edges in it. So I start at the bottom here. What happens if I take the right-hand rule? What I want to happen is I walk the outside of the void. Right? But instead, what's going to happen is it's looking pretty good. Go here. Ow. 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 We didn't explore the outside of the void there. Right? So what are we going to do about this? It seems intuitively like the crossing edges are a problem. How are we going to get rid of those without? Now I start taking edges out of the graph. That means I could break the network apart. So how am I going to take edges out of the graph and still only know where my single hop neighbors are without partitioning the graph? So when I was visiting ICSE, I discussed this with Dick Karp, who, by the way, is no relation to me, although several computer scientists have tried to suggest that he is at various points, to me usually. I should say, to my knowledge, Dick Karp is not related to me. So what he said is, oh, you know, this sounds something like planar graphs. I don't really know much about them. Why don't you look into what planar graphs that are well-known are? And it turns out he saved my bacon. So there were these two well-known planar graphs, one from pattern recognition and one from zoology, if you can imagine that, about how to construct graphs that didn't have crossing edges in them. And they go very simply like this. One's called the relative neighborhood graph. If you've got an edge here, UV, and you want to ask, should I keep it or get rid of it because it might be in a crossing? What you do is you ask yourself, in that gray shaded loon there, do I see anybody else who we'll call a witness W? And if you do, great. You intuitively think, I can get to V via W, so I'll get rid of the direct link between U and V. Similarly, on the right, you can do the same, but use the circle whose diameter is UV. If you see a witness inside, get rid of UV. And this only requires you to know the positions of your single hop neighbors, and it can be shown not to partition the network. I leave the proofs for another day. Just to give you some intuition of what this looks like, if you have a 2 kilometer by 2 kilometer region, plunk down 200 nodes, you get a bird's nest of just who's in range of whom. Then the Gabriel graph gets you this, very beautiful faces with no crossing edges, and the relative neighborhood graph gets you this. So this is starting to sound promising. So the basic plan is going to be root greedily when you can. When you see that there's no neighbor closer than yourself, use only the subset of the graph that doesn't have crossing edges in it. And do it like this. The example I'm showing you, greedy, would work, but it's easier to show how this works in a topology like this. If you're at X and you want to get to D, notice that perforce, the line between X and D, the imaginary line between X and D must, if there's a way to get to D at all, must cut some series of faces in the graph. So all we're going to do is just walk using the good old right-hand rule around each face. Each time you get to the next face along that imaginary line, hop onto it, and eventually you'll get to D. Now, just to be clear, when greedy works, you use greedy on the full graph. This is just a pedagogical example. But if you had a case where there was no neighbor closer than yourself, you could just do this. Each time you hop onto the next face, and eventually you'll reach the destination. Okay? This is scalable geographic routing. It gets you state at each node independent of the total number of devices in the entire network. So O of the density rather than the total scale of your network. So we didn't stop there. Together with Youngjin Kim at USC, Ramesh Govindan at USC, and Scott at ICSE, we worked together on building this thing. That's a little computer, a sensor moat about the size of a 10p piece, or a quarter if you're American. And it's got a radio and a CPU and a tiny little bit of memory. And we built it. We ran it on 2 50-node test beds. And it didn't work. We found that only 68.2% of the arbitrary pairs of nodes could reach each other, even though we knew paths existed in the underlying network. So what is going on? Well, it turns out that the radio ranges in real deployments are highly irregular, and that those constructs for making planar graphs that I showed you have some weird monotonicity assumptions in them about if there's an edge that exists with some length, then every time 2 nodes are closer than that, that edge must also exist. And wireless networks ain't like that. Okay. So what did we do? This was doubt happening here. We found when we looked deeper that GPSR's naive planar graph just chopped the network in half. It was cutting edges that it shouldn't cut because of the violated monotonicity assumption. So our response was to completely retool our algorithmic research. We changed the algorithmic problem we were solving, came up with a completely new algorithm because we did experiments and saw how things really behaved. And what we did was we came up with CLDP, the crossing link detection protocol. Doesn't assume uniform radio ranges. In fact, it assumes nothing at all about the underlying radio graph. And we found that it worked perfectly. We had 100% of the node pairs connected. So I'm going to give you a quick intuition about what CLDP does. It's quite different than the Gabriel graph or relative neighborhood graph. We actually send packets on tours to discover crossing edges. So what we do is, let's say we initially start out with a full graph, and every link is marked as you can use it. It's routable for perimeter mode. And what we're going to do is send a packet on a tour from D to A with a query inside the packet. Are there any crossings of edge DA? And then you use the right-hand rule to forward this. And as it goes around, nodes will notice if there's going to be an edge that crosses DA, and they can write into the packet that they've seen one. And then the probe will eventually return to the originator, and the originator can decide to take action to eliminate one of the two edges, either locally or send a message to the guy at the other edge to tell him to get rid of the crossing edge. Okay? So this seems cool, but it's harder. It turns out that there's a funny type of situation in a graph that I call a cul-de-sac, which I believe is in wider use in the United States than in the UK on the basis of teaching lectures on this. What a cul-de-sac is sort of a dead end. But in a graph, I would call a cul-de-sac, well, this is a dead end, right? It's connected to the rest of the graph, but you can't go anywhere else. But even if there were a subgraph that were down here, that itself in its entirety would be a cul-de-sac. It would be singly connected with the rest of the graph. Okay? So if you have a cul-de-sac, that's going to be an edge you'd better not remove, because that edge is the only edge connecting him to everybody, right? So you can deal with this. You send packets on probes, on tours, like before. You'll notice that because the probe came back on the same edge to B that it went out on, that's a sign of a possible cul-de-sac. So you say, I can't get rid of that edge. Okay. And then in this case, on the left here, you can just get rid of AD instead, right, which won't partition the network. Uh-oh, what about this guy on the right? Here's a crossing where both guys, C and D at the bottom, are cul-de-sacs. So you can't get rid of that crossing. The old tour comes back on the same edge. Tour came back on the same edge. I can't remove that crossing. Okay? So it turns out that, much to our surprise, if you do this and leave in the crossings like that one, you can prove that GPSR will always work on the resulting graph, that crossings like that don't break perimeter mode in GPSR. So if you combine GPSR minus the broken planarizations for real-world networks and sub in CLDP, you get provably correct scalable geographic routing for any network, in fact, wired or wireless, because now there's no constraint on where the edges, how long the edges may or may not be. In wireless, we were sort of thinking, oh, there's a geographic constraint. So stepping back from all of this, GPSR is kind of a pure algorithmic result, as was CLDP. But CLDP was backed by experience. In terms of adversaries and doubt, right, we realized that the irregularity of radio ranges meant we had the problem definition wrong. And that led us to a completely new problem and a completely new algorithm. And the way we did that, the way we figured that out, was by embracing details, experience with real-world link behavior. And this confirmed that, in fact, a workload that we thought was kind of adversarial and not real was common. Okay. So I'm going to switch gears and talk about capacity now for a moment. So 802.11 is what a lot of systems people, I think I first heard this from David Culler maybe, is a success disaster. Everybody's using it, and then it stops working. So it's great if you've got a Wi-Fi AP and you've got a laptop and you're pretty happy. Then your neighbor gets one, and he gets a laptop, and you're still kind of happy. And then everybody gets one, and you're starting to get less happy. Not because they're watching cat videos too, but because you're all sharing this fundamental resource. You're all sharing the wireless spectrum. Right? And so there's interference. So how do Wi-Fi networks deal with this sort of shared spectrum? Well, the basic technique that Wi-Fi uses is called carrier sense multiple access, or CSMA for short. Say you've got two APs on the left. Each has its own client, which is horizontal from it. Okay? And if AP1 sends to its client C1, it will also, it radiates omnidirectionally. It will interfere at C2. So C2 will hear AP1. So carrier sense multiple access is, oh, no problem. When AP1's sending, only AP1 sends. AP2 takes a turn, and he'll interfere at C1, and they take turns. Okay? This means hosts only transmit half the time. The APs each only send half the time, which of course means that each AP gets half the throughput if it were alone. Right? You could do a little better, maybe. Try to improve your throughput by making sure that your client hears you well. You can do something called transmit beamforming, which just basically means use your multiple antennas at the AP to try to steer your energy to reach your client. But that still leaves interference to the other guy. It's agnostic about the other client. Okay? You could try to do more. There's tremendous excitement in the research community about this technique, which is nulling, which is that you actually, when AP1 sends, he sends to client 1, and using the appropriate signal processing and linear algebra, arranges for his transmissions to cancel each other so that they're notionally, hopefully, zero energy received at C2. So you actually null out. So C1 hears, but you constrain what you send so C2 doesn't. If you could do this and it worked well, then AP1 and AP2 could send at the same time, right? Because C1's not going to hear AP2, C2's not going to hear AP1. Kumbaya. Right? So both hosts transmit 100% of the time. So we thought, let's try this out. And I just want to say, a lot of great systems research starts with, let's try this out. Like you read a paper, and you think, this sounds pretty good. And so you build your own, and you can't believe what you find. It's amazing that this is a good strategy for systems research. Just read about something and try it, and you've got a whole research direction. But it's true. So we tried it on the 7th floor of our building. We placed nodes around and used 30 topologies with nodes placed in all different places. This is a CDF of the aggregate throughput we got when we tried comparing taking turns, CSMA, and nulling. So what we found was that CSMA did about this well. That dashed vertical line is the best CSMA could ever do. This is the aggregate throughput of the two sending APs. And nulling did like that. Worse than taking turns 80% of the time. So what's going on here? In order to understand this, we need to teach you one slide of EE. Bear with us. Are there any EE people in the audience? There's a quantity that helps you think about how well you are heard, or how well you're understood at a receiver. Signal to interference plus noise ratio, SINR. It's very simple. As I speak to you, that's the signal. If somebody else were talking at the same time, thank you for the example, Noah. I planned that. That would be the noise. It would be the thing that you're not trying to hear. And so based on the relative magnitude of the signal and the noise, you will be able to understand better or worse. Right? The higher the signal to interference plus noise ratio, the better you'll be able to understand. The faster the throughput you'll decode. And the lower the throughput you'll be able to decode. So when we tried to measure SINR, here's what we found. When we beamform from AP1 to C1, which does not try to null, this is what we found for the strength at C1 of the signal of interest and the strength of the interference coming from AP2. So the ratio between them is quite small, and that's why nodes take turns in Wi-Fi. Right? If we did nulling, good news, we found that the ratio between the two improved. When you null, you add constraints to the way you radiate, and so it also reduces the signal of interest. But it cuts the interference more, and so you get a ratio improvement at C1. Right? Now you might say, wait a minute. You promised me, I didn't promise you, but I suggested that the interference would go to 0. That's what nulling was about. So why is that there? And you know, hardware sort of sucks, right? I mean, like there are all these imperfections in the hardware noise that comes from components. They don't radiate exactly what you thought they were going to. Also, you have to take measurements of the behavior of the channel that get stale over time, and that will mess things up a little bit. But also, this is not telling you the whole story. These measurements are averages of the power received at each client. But Wi-Fi radiates over a 20 megahertz frequency band. So let's try to zoom in and see what's happening at a finer granularity in that band. So these little chunks of Wi-Fi are called subcarriers using a multiplexing scheme, modulation scheme called OFDM, orthogonal frequency division multiplexing. If you look at that receiver at the top there, when you beamform from the AP at the top left to the guy at the top right, that's the SNR, there's no I because there's no interference in this, across subcarriers. So pretty flat-ish. Then, when you try to null toward the other client, what winds up getting to your own client is much more variable across subcarriers and power level. And this is just because of the constraints mathematically in the system. As you try to enforce that you null toward the other guy, you have to give something up on some of the subcarriers yourself. And then, if you have the other guy come in and do nulling, his residual interference adds in, and then you get this horrible thing. Right? So this is the picture for when they're both sending at the same time with nulling. Right? So what's the consequence of this variation? Well, it kills your throughput, unfortunately. Why? The answer has to do with how Wi-Fi works. In particular, Wi-Fi sends redundant information because it knows that some of the bits may be corrupted on the way to the receiver. But it chooses an amount of redundancy to send. And Wi-Fi uses only one information rate and one redundancy rate of coding. And that applies across all of the subcarriers in Wi-Fi. It's for cost complexity reasons why they build Wi-Fi this way. Okay, so if we look at what happens, what's going to happen is on some of the subcarriers, the SINR is really low, so we're going to get lots of bit errors. Wi-Fi sends the bits of your packet separately on different subcarriers, actually. And so on some subcarriers, there'll be lots of corrupted bits. And on some of them, you're going to be, that's very dark, sitting pretty. There'll be good subcarriers where there'll be very few bit errors. But what's going to happen is that Wi-Fi is going to have to pick a modulation that is going to let the packet get through with no bit errors overall. And so it's going to pick a low bit rate to send at. It's going to be hamstrung by the worst of these subcarriers. So maybe, is there some way to reduce this variation? Intuitively, you sort of pick a line and say, well, some subcarriers are doing really well. Maybe they don't need to do quite that well. So what I'm going to do is take from the rich and give to the poor. So I'm going to try to sort of take the peaks and spill into the weaker subcarriers, and then we'll flatten things out. And if I can do that, maybe this line is high enough that I can send at a higher bit rate than if I were targeting the bottom of that valley, which is what Wi-Fi does today. Right? So we're done. No. That's only half the story. This is the SINR at the top right guy. But this whole thing, both APs, the top and the bottom, are both going to have to do. So decisions about spilling power between subcarriers, both APs need to do. And so if you do this independently, if just each AP is just thinking about, flattening out at its own client, you get a mess at the other guy's client. And so you need to do this jointly. And this is what Yorgos Nicolaides, my student, did and published in CoNext 2015. In a somewhat 70s reference, called it COPA, Cooperative Power Allocation. I guess that must be my reference, because I don't know how old Yorgos was in the 70s, really, but, or if he existed in the 70s, in fact. Minus 10, all right, there we go. So there's a MAC protocol. What it does is it figures out which APs can cooperate, and the APs exchange enough information for them to mutually do power allocation. Each AP needs to know what's happening on the link to its own client, the link to the other AP's client, and vice versa. So we exchange that information. The AP pair then distributedly, without talking any further, runs the same algorithm locally to reach a cooperative solution in lockstep. This is almost like state machine replication. Like you synchronize the state at the beginning, and then they proceed in lockstep. Okay? And after you do this, hopefully you'll be able to use a higher bit rate, and then you get higher throughput. And COPA incorporates the fallback that if you try this and you find it doesn't get you higher predicted throughput, you can always fall back to taking turns if that does better. That's your fallback. So you should never do worse than CSMA. So I'm not going to describe the detailed algorithm for you. But the good news is this is what happens when you do it. First of all, if you do nulling by itself, this is a plot across subcarriers of when you do nulling, what the bit error rate, and it's more bit errors at the top and fewer bit errors, exponential, at the bottom. You get widely varying bit error rates across subcarriers with vanilla nulling. COPA nicely reduces the variation in bit error rate. And another feature of COPA is that if it sees that a subcarrier is just not going to work out well, it will actually just stop using the subcarrier. Notice these very high bit error rate subcarriers. It says, that's a lost cause. I'm better off giving that power to some other subcarrier. Okay? And because it does this, it gets you higher bit rates, right? COPA achieved, in this example, 32 megabits per second, and legacy nulling got 12. Okay? So let's repeat our bake-off. This was the state of play before. COPA actually gets you to a point where you recover the promise of nulling for 50% of the topologies in the CDF. And you never do worse than taking turns, because you can always fall back to that. Right? So stepping back from COPA, this is getting repetitious. For adversaries in wireless, we find that when you interact with the physical world, the workload becomes quickly adversarial, the way things behave, not the way you expected. The nuances of low-level subcarrier behavior turned out to matter a lot. And I think this work is a great example of something that I heard Satya at CMU say a lot when I was there, which is that Herb Simon at CMU always used to say the job of a systems researcher is to produce phenomena and explain them. It sounds so simple, but it's just a fantastic place to start. Okay, now we're going to shift gears and briefly talk about network and system security. So we'd like to protect sensitive data in networked applications. So we got a client, we got a server, we got some kind of internet in between. Oh, that is not good. Just a moment. Am I doing slide timings? Just a moment. Right. So we're going to protect sensitive data in network applications. Oh, no. Right, OK, better talk faster. We're going to protect sensitive data in network applications. Who's doing that? And so we've got network apps like banking systems and SSL web services. And we're going to have all kinds of sensitive data in these systems, bank credentials, health data. Right? The NHS was supposed to go completely online. That didn't happen. Well, someday they'll go online with health records. Maybe it's good they didn't. That's what this talk is sort of about. And so we want to protect the sensitive data, even though it's stored on both the client and the server. So our cryptographers have shown us how to make attackers unhappy. If an attacker eavesdrops in the middle of the network, they can't successfully decrypt what's sent encrypted if you use the crypto correctly, which turns out to be quite difficult. And they can't tamper with the data. And there's all these great protocols, SSH, IPsec, SSL, TLS, that do this in the middle of the network. But we want to ask a question. As you may have heard if you've read a newspaper in the past couple decades, there's a lot of bad, vulnerable software out there that can be exploited remotely. And so if an attacker can inject his own code, which is what an exploit lets you do, into the server and the client, today, he's going to be pretty happy, because then the sensitive data are just sitting there. He couldn't hear it in the middle of the network, but he can see it on the server. Good strategy. So when you see this, you say, oh, the software is going to get better. Surely vulnerabilities will be eradicated. So this is a plot over time of the number of critical vulnerabilities that have been reported by year. So to be fair, you're saying, oh, God, things are getting worse. Well, it's sort of like trying to diagnose cancer. It's not that people are getting more cancer. It's that we're finding it more readily. We're looking more closely. Right? But on the other hand, it certainly seems that an era of vulnerability-free software seems rather elusive. So let's try to take a principled approach. Can we build software that doesn't disclose sensitive data, even if somebody exploits it successfully? So how are we going to do that? let's assume successful exploit of today's vulnerable network applications. What guarantees do you get now? Well, today, not that much. The old problem is that applications are monolithic, that they're one unit, all the code, and can freely read and write the sensitive data at the top there. Okay. And that dark shading means that we have to trust the code. We have to trust that it's going to work correctly, or bad things can happen because it can read and write sensitive data. It's privileged. That's what the gray shading means on the code oval. Of course, if somebody exploits, they inject their own code, which can then just read the sensitive data and send it to the bad guy. So monolithic applications, bad idea. This is very widely known. Niels Provost in 2003 suggested that maybe we should actually take Salzer and Schroeder's advice from 1975, which was the principle of least privilege, divide your code into modules. For God's sake, give each module as little permission to do things as possible so that there's less chance for things to go wrong. Salzer and Schroeder were thinking about bugs. Vulnerabilities are a kind of bug. And so now what's going to happen is if an attacker can inject his own code into the unprivileged code, you've partitioned your applications but can only read non-sensitive data. So he's unhappy, the attacker. The sensitive data he can't read. If, however, he can exploit your privileged code, your trusted code, then he's going to be happy because that module can read the sensitive data. So this is sort of a way forward if you can chop things up. So the question is, if you do what Provost said, what kinds of guarantees do you get? And so it turns out the main thing Provost was thinking about here was preventing attackers from becoming root, from becoming super user on a machine. He wasn't thinking much beyond. That was a huge step forward at the time. So here's a new attack that my student Peter Marchenko at the back of the room there discovered when he was here before he graduated. He's now at Google. He discovered this session key disclosure attack. And so let's say there's an attacker who's on the physical path between an SSH client and the server. Here's what the attacker does. He exploits the unprivileged process, which can't read sensitive data. Then what? Then there's the key exchange protocol between the client and server. And it turns out that what the SSH software does is that the unprivileged software then winds up with the crypto session key for the whole session. So then the attacker just sends it using the code he's injected. He now has that. Now the session starts. User authenticates its SSH using that session key. Now the attacker has the password. Then the whole session happens. It's encrypted with the compromised session key. The attacker has all the session data. The problem is, for some reason, the session key is not treated as sensitive information. Okay. So a solution is trying to chop up things even more finely, according to the principle of least privilege, so that untrusted compartments don't have access to things like session keys. So we did some work. Andrea Bittow, who is Mark Handley's and my PhD student, and Peter Marchenko together worked on Wedge, which was an architecture for exploit-tolerant servers, servers that didn't give up sensitive data when they were exploited. And we did this for Apache and OpenSSL and OpenSSH, and along the way created some new primitives for Linux that made it easier to build things like this. A nutshell result was that using Wedge on Apache with OpenSSL, which is a big, horrible code base — you can ask Peter just how horrible it is at the end. I think he's still scarred. Is that we reduced the amount of code that had access to sensitive data by 90%. So you can think of that as the chance, if bugs are sprinkled uniformly throughout the code, they may or may not be. That's 90% less code that could get exploited, potentially. No access to, or that could get usefully exploited. No access to sensitive data anymore. There's a modest performance penalty of 6 to 23% versus running the completely monolithic, non-secure Apache OpenSSL. OK, so what about privacy in today's main application platform, the web browser, which will be the final research piece I'd like to discuss briefly. So in case you, again, haven't been under a rock for 10 years, the web isn't pages anymore. The web is applications. So early websites were static documents. You can identify ace computer scientists because they learned of the web in 1995 and still have pages that are static documents. Look at all the Mark Weiser Award winners, really, really dinky web pages. So the browser retrieved a file and displayed it. Today, we use web applications. So the page actually contains code that your browser downloads and executes without consulting you at all, I might add. Why is that OK? Who knows who wrote that code? And another thing is that web app developers constantly just grab code from other web app developers. Why? Because it's all open source. Your browser downloads it when you run the app. This is like the web is sort of the apotheosis of open source. Everything is visible. All the code is visible to everyone, right? So maybe we should be concerned about privacy in this kind of environment. Apps have sensitive data all the time. The JavaScript developer could be totally malicious, right? Each site has code, even if the site developer is not malicious. Maybe he borrowed code from somebody who was malicious when he's out finding libraries to use. Should you run programs presented to you by parties you don't trust? Your browser does it all the time. And it turns out there's an even bigger problem. Your browser is almost like an operating system. Don't tell Microsoft I said that. But you visit multiple sites in different tabs. And those are almost like different applications in today's browser, right? So what happens when you do that? Well, here's an example I perhaps appropriately in London like to call bad weather. You've got a browser. You open two tabs. One's your bank. One's weather.com. You're looking at this. You're enjoying yourself. And what if it turns out that somebody at weather.com includes some malicious JavaScript that just decides it's going to, in your browser, it's all one browser program, read your bank statement and send it to weather.com's server operator. Why can this not happen? Well, the web architecture thought of that problem. There's something called the same origin policy, or SOP for short. What happens today is that a script running in weather.com is isolated on the basis of the domain name you downloaded it from, which is called the origin, weather.com. The SOP says a script from weather.com can't read data from barclays.co.uk. That's the same origin policy. So intuitively, yes, this is a form of discretionary access control. Discretionary access control just means that either you're allowed to have the data or you're not. Once you have it, you can do whatever you want with it. But it turns out that DAC is really problematic. This is sort of the narrative of systems that are intended to be secure often create problems for flexibility. I'm going to try to show you it doesn't have to be that way. But often the system tries to stop bad things and stops you from doing non-bad things also that you should be able to do. So it's too permissive because third-party code under the same origin policy actually can leak sensitive data. If you use certain kinds of scripts and put them in a script tag on a page, the SOP doesn't apply. And there are various reasons for that. Some scripts are written to be able, because they want to be able to look at what's in the enclosing page to do useful stuff. So that means that if you enclose a script in your Barclays page in a script tag, it is allowed to leak, not in a separate tab in the same page. The Barclays developer does that. It can leak to, say, evil.com. And that's because things in script tags run with the enclosing page's authority. So it's too permissive, but it's too restrictive at the same time. It turns out that you're not allowed to read cross-origin data if you are in different tabs. So imagine that Mint wants to have a JavaScript app that runs in your browser that's going to read data from chase.com, that bank statement, hsbc.com, that statement. And the SOP says that a script from that origin is not allowed to read data from XML HTTP requests that come, responses that come back from those different origins, which means Mint can't do this. So what does Mint do? We'll get to that a little bit later. It's a little upsetting. I hope you're ready. So the problem is that discretionary access control is too brittle. You either have to give up control of your data or deny access completely. So can we achieve privacy for the user and flexibility for the developer? So DAC forces this choice between privacy and functionality. Mint, which I've already described, can't be done as a secure third-party mashup for the reason I already explained. A script from mint.com. What are we going to do if we're the browser? With a policy decision, the SOP would not allow it. But what else could you do if you wanted to step outside the SOP? So if you want to choose privacy, banks could block mint.com from reading their data. There's a mechanism in modern JavaScript specs that would actually allow banks to inspect the origin that sent them the request and deny sending a reply. Okay? That's privacy. On the other hand, the user might say, no, I trust Mint. I want to run the app. On the other hand, functionality. The banks could say, OK, here's all the user's data from the bank account. And then the script from Mint can violate the user's privacy. It can send the data anywhere. So in this unpalatable choice, how does Mint really work? Mint, when you sign up, asks users to give Mint's website your bank login credentials. And then it pulls the data to Mint's server, and then just does it all on the server side and sends you the result. This is really, really nuts. I mean, and the reason they're forced to do this is because the same origin policy won't let them do it in the browser. So you have to give up your login credentials to Mint, which stores them somewhere. It's amazing that Mint has 10 million users more. So what are we going to do? There's a germ of a solution, and that's what we call confinement, a very old idea from Butler Lampson in 1973, but it's proven very elusive in practical systems. We're going to let the untrusted code JavaScript from mint.com in the browser read the sensitive data, but somehow, once it's read the sensitive data, you put it in a strongbox, and it's not allowed to talk to the outside world anymore. It can render in the browser, but it can't talk to the outside world anymore. So it turns out that when you want to do things in the browser, you can ask Peter Marchenko about this also. Life is very hard. First of all, web developers don't want to learn a new language because they like JavaScript, or maybe they don't like it, but they just don't want to suffer through learning something else that's even worse than JavaScript. And it turns out that if you go to a company like Google and say, I'm going to make your JavaScript engine really secure, they say, well, it's really fast, and if you add even one instruction to the code path, I'm not going to let you do it. And that's crazy, but it's reality, because there are these crazy browser wars between browser vendors where they publish meaningless benchmarks about how many microseconds it takes to do something, and they don't want to have a worse number in that table. And you've got to keep familiar concepts in place for web developers if you're going to try to improve the browser, which means using origins as principles and keep the constructs in the page, iframes, pages, and so on the same. So one slide describing what Cal is as a design. Cal gives you confinement in today's web browsers. What an origin can do is label data just with a string that the origin that deems the data sensitive can label it. So Chase labels its data chase.com. And then you might have a label that has a conjunction, label chase.com and hsbc.com. That's where you wind up if a script has seen data from both. That winds up being the current label of that executing script. And then you allow cross-origin sharing, turn off that part of the SOP for scripts that opt in, and then the user opts in. But when a recipient reads data sensitive to foo.com, the browser runtime makes sure that the script loses the ability to communicate with other origins. The browser runtime enforces that. So Mint works in Cal. You have the script from mint.com. It reads labeled data from chase.com. The browser enforces that after mint.com is allowed to see the data, as it's allowed to see the data. Sorry. The script in mint.com gets the data but doesn't look at it yet. It then gets the data from hsbc.com that's labeled and doesn't look at it yet. Before the browser will let the script from mint.com look at the data, it requires Mint to so-called raise its label. So Mint has to raise its label to include chase.com, which means it can't talk to anyone but Chase after that. And then it's allowed to read the data labeled chase.com. Then it raises its label further to Chase and hsbc.com, and now it can't talk to anyone anymore. And now it can read the data from hsbc.com and show pretty graphs to the user. So this gets you flexibility and privacy. We emphasized deployability in Cal. The main thing I want to emphasize is that it's fast. Cal only increases worst case page overhead for page loads by 16 milliseconds. How did we pull that off? By trying to master the complexity of the layers of the browser and understanding all of the complexity of the browser. It turns out that we don't track labels during JavaScript execution because that would slow scripts down. All we do is have to make checks when you cross a protection boundary in a page. When one browsing context talks to another, we have a gatekeeper only at that boundary that says, are you allowed to go across that boundary or not? Which, by the way, is how the SOP is already implemented in the browser. So, and it's backward compatible with legacy web pages. I'm not going to regale you with all the cool apps you can build with Cal, but it's not just for third-party mashups. We're getting some interesting press when we released this open source. We got written up in Network World and in Gadget, and somewhat to our fear, but they were nice to us, the Register. They were quite positive about the system. I had a really interesting time talking to their journalist. And I'm very pleased to say we've standardized CAL at the World Wide Web Consortium. There's now a first public working draft, CAL standard, which you can go read, and please file errata against it. And this is on the path to getting this deployed in real browsers. OK, so I'm going to wind up. What next? I've been told I should try to say something about the future. And there's no more inaugural like this for me ever again, I suppose. So you can't come back and tell me I was wrong. Haha. So what's the next threat in system security? Let's say we achieved fabulous success in making servers exploit-tolerant without giving up sensitive data, and browsers supported confinement. What threats would remain? In other words, when we closed down the easy things attackers do today, what would be the harder things left that they would need to do? One thing is side and covert channels. One very interesting nuance about this is that if you use discretionary access control, side channels should only ever exist in the hopefully small trusted privileged code that you have, because that's the only code that sees sensitive data. But they can be accidental. There's an awesome, how many of you heard of the operating system 10x? This is an age test. Right, OK, so there was a great operating system for the PDP-10 that had a side channel in it that would leak passwords to anybody who could run a program. And this was by timing how long it took for a system call to return on the basis of whether there was a page fault or not. You could figure out how many characters of the password were being matched. So you could linearly guess. Just try the first character one at a time, and if when it took longer, then you knew that it moved on to the second character to compare. And so you got the first character right. Boom, exponential to linear search. So that's one kind of side channel. It's very easy to make a mistake like that. And confinement can have side and covert channels. One worrying thing about confinement, I'm nothing if not honest. Confinement does mean that covert and side channels can exist in untrusted code. When you confine untrusted code, it could have been written by a malicious person. And the covert channel they could put in is now that they're not sending sensitive data. They're just sending innocuous data at time intervals that modulate what your sensitive data is. Right? If you want to be very afraid and stop using computers, you can look at other kinds of side channels, like Shamir's fantastic result from 2014, which is that ultrasonic sound from the voltage regulator in your PC will emit noise that leaks your RSA key to attackers who can hear it within 4 meters. So I would say that this is not doom and gloom. The world would be, we would have made so much progress if we got to a state where this was what attackers had to do, was find side channels or covert channels. We want to close the gaping holes first. I think there's a huge opportunity in system security because least privilege design has great synergy with program verification. Why? Because least privilege design is all about shrinking the size of your trusted code. And verification, that is trying to do mathematical proof about the properties of a program, gives strong guarantees that code is correct, but it sometimes scales poorly when the code gets big. So this sounds like a match made in heaven. The trusted code in your system, you try to make it small, principle of least privilege, and now maybe instead of auditing it with your eyes, try to verify it. It's small, so the verifier might complete. Right? Another interesting aspect of this is designing for verifiability, trying to design your system with modules that are amenable to verification. There are a couple examples I can't actually go into for the reason of time. If you're curious, look up Morisset's SFI verified verifier from PLDI 2012, or Zeldovich's very recent COC verified file system for Linux. How might wireless networks evolve? Today, if you ask people, how are people going to get online wireless, they say, oh, it's easy, there's LTE everywhere. Really? Even in central London, my 6th floor UCL office has terrible LTE coverage. or even phone call coverage, actually. I don't know what they made that building out of, but usually they build to cost and the materials aren't so good. But it's also really uneconomical for a cell provider to ensure that cell towers are within one-hop range of all users in a city. So maybe we could eventually start to see using multiple wireless hops to improve performance in situations like this. And I'm going to really stick my neck out here. Maybe by 2020, self-driving cars and control loops among self-driving cars might get us into an era where you actually had direct wireless node-to-node communication. And the truth is, I do not follow conferences on multi-hop mobile networking anymore. There's been a huge amount of work in that area, and it lacked a compelling application. It might be that we finally have a concrete commercial application that could make something like geographic routing with many devices in mobility take off. So I just want to point out that it's an awesome time to work on systems and networking. If you want to change area, please come talk to me. We've seen the ascendancy of software. We've got networks that are hackable now. It used to be you bought a box from Cisco. It had application-specific chips inside of it. You couldn't change them, and they just did what they did. Now, if you want to do wireless experiments like Yorgos, you actually have a radio that you can just write code for. You don't have to change silicon at all. This is a huge enabler. Nobody would be doing work like COPA without software-defined radio. And commodity PCs can actually compete with routers now, and they have open source networking stacks. Performance-wise, they can compete. And in the data center and networking, we're starting to see centralization, which means that you can actually start trying to do ambitious things algorithmically about how you run your network that you might do centrally, like Nikola Gvozdia at the back of the room there, actually even outside the data center and more distributedly. You could do things centrally that you would never attempt distributedly because it's so hard to run distributed control loops. And we're starting to see that. So it's a very exciting period in networking. Also, if you're a systems person, we keep having more and more layers of abstraction, and that just means more and more opportunities for great systems research where you can understand all the detail from the top to the bottom. This year we had, at SIGCOMM, it used to be the case, the premier conference in networking, it used to be the case that there was a huge community of people who came every year and were working on the same exact problems. And they would, in a good-natured way, give each other hell at their talks and really try to dig into, are we really going to solve this hard problem? Are we ever going to have congestion control that works for the global internet? And then people kind of all went off in their own directions. But sometimes when a new technology comes along, we get that old-time religion back again. And we see that there are competing groups trying to solve the same problem because of that new technology. Like if you have RDMA, this extremely low latency interconnect in data centers, how do you do TCP, the congestion control protocol for the internet over that? And we had dueling papers from Microsoft and Google last year, and they built competing schemes and asked each other really hard questions at the talk. And of course, you could also imagine even the web, talk about a stack. Oh my God. You've got JavaScript code bringing in objects from all over the internet, running on top of one of 3 different HTTP transports, on top of TCP or maybe multipath TCP, on top of 802.11 with an LTE interface on the side. How do you make that ensemble from top to bottom perform? So to wrap up, I've discussed for you how the next billion devices and wireless users coming at the internet's edge are going to make it hard to scale in the future. In routing, that's as the number of destinations increases. In capacity, there's more interference, and you need to find a way to keep pace. I talked about approaches to scaling of geographic routing for the first and cooperative power allocation for the second. And I hope you have principled fear about the problems that ubiquitous connectivity brings for attacks on users' privacy. And I talked about exploit-tolerant software and confinement with Cal for the browser. I hope I've conveyed just a little bit of what systems research is as a discipline in terms of drawing heavily on algorithms, adversarial thinking, doubt, and embracing detail. And I believe that these pressing challenges are going to keep the systems and networking research area vital for a long time. And I'll say one more word on that. I think the other thing that keeps systems vital as a discipline is that we're a very big tent. As long you can come to us with algorithms, you can come to us with programming languages, techniques. We want it all, as long as you've done your due diligence on that adversarial workload and how things are going to work out in practice. That's the key. And I think I'll conclude there. Thank you.
Thank you, Brad. And I would like to invite Professor Scott Schenker to deliver a vote of thanks.
Feel naked without PowerPoint. So I'm very grateful for this opportunity to express my vote of thanks, a tradition with which I was not previously familiar, and my remarks may reveal my ignorance on that score. I want to start by acknowledging Brad's wonderful talk. This was a talk that not only explained the what of some of Brad's many research accomplishments, but most artfully illuminated the how and the why that underlie all of Brad's work. However, I traveled all this way not just to comment on his talk, but to make a larger point. When I first became interested in networking, the internet was in its pre-commercial infancy, and the people who worked on it viewed it as a calling. But in the years since, in networking and in systems more generally, academia has become so obsessed with publication counts and citation rankings that we often lose sight of the underlying motivation. In short, for many, it has become merely a career. But Brad is a rare throwback to that older era. For him, education and research remains far more a calling than a career, and this difference pervades everything he does. As Mike's introductory talk made abundantly clear, Brad is exceptionally devoted to mentoring individuals and to helping the community at large maintain high standards. But Brad also applies these high standards to his own research. In our various collaborations, he was never satisfied with a superficial understanding. If it was a theorem, he needed to review the proof in detail. If it was a simulation, he needed us to run more corner cases. And if it was writing, well, let's just say that very few words of mine have ever survived into the final text when Brad was my co-author. More crucially, Brad also applies these high standards to problem selection. He never settles for least publishable units, but instead seeks out the most challenging problems facing our field. His early research asked the fundamental question, how can we scale wireless routing? And his answer involved an ingenious and revolutionary approach, one where sweating the details of planarization, something no one else had done, made all the difference in practical settings. He has since gone on to ask another deep and urgent question, how can we make software secure? He started with groundbreaking tools like autograph and polygraph that surpassed all existing techniques. And he has continued this daunting quest by developing browsers that provide the long-sought goal of confinement, but in a way that, for the first time, is fully compatible with modern web usage. These are only two examples, but throughout all his research, Brad pushes his designs to have scalable algorithms, to be fully robust, to function under real-life conditions, and to withstand the harshest environment of all, his own relentlessly questioning mind. As a result, his work is a model for how to do research the right way for the right reasons. You may think these comments about Brad merely reflect my bias, but in writing this talk, I contacted several colleagues in an attempt to get some dirt on Brad. To my great disappointment, none were forthcoming with anything scandalous. But they all describe Brad as a scholar in the old sense of the word, one who relentlessly pursues truth and dives deep and dangerously rather than comfortably remaining in the shallow end of the research pool. As for why we are gathered here today, I must admit that the byways of British academia are foreign to me. But as I understand it, the inaugural lecture is held to belatedly celebrate the promotion to professor. I find this ironic because the word professor comes directly from Latin for a person who professes to be an expert in some art or science. Brad does not profess to be an expert. Universal understatement and constant self-doubt are more his style. He lets his work speak for himself. A better word for Brad is educator. The root for educator is from the Latin ducare, meaning to draw out or to lead. Brad draws out the best from us by insisting on the highest standards in his work and in ours, by generously mentoring those around him, and by working tirelessly for the community. And he leads the field by performing vital research that is always imbued with important insights, great depth, and infinite care. To repeat Eddie Kohler's words cited earlier by Mike, Brad is committed to an ideal vision of the research life. But for Brad, this ideal vision is not an abstract notion. He lives it every day. Brad doesn't do this for fame or fortune. He does it because research and education are his deep and abiding passions. And for this, we owe him our vote of thanks. To Brad, with gratitude and admiration.